Hello everybody, and welcome to page 23 on the workbook. And on this page, what we're going to do is to develop a second formula for the equation of a plane. We already talked about one formula earlier that had to do with slopes of the plane in the x and the y direction, and we're going to come up with a second formula on this page. Okay, and this particular formula for the equation of a plane is going to have to do with something known as a normal vector to a plane. What do we mean by that? Well, a normal vector just means any vector that's perpendicular to the plane. Okay, so if you take the plane that's shown in the picture down here, a normal vector would just be any vector that sticks off perpendicular to that. Okay, so let's assume that n is a normal vector. And let's also assume that we know the value of that normal vector. So maybe it has components a, b, and c, ai plus bj plus ck. And we're going to also assume that we know the value of one point on the plane. That's this p naught that we have here. So we'll assume that x naught, y naught, and z naught are actual numbers that we know the value of. Okay, and it's our goal here to derive a formula for the equation of the plane based on this information that we have. So to get started in this process, think of this point P, x, y, and z as being just some arbitrary point on the plane. If we can describe a formula for that x, y, and z, we've found an equation for the plane. Okay, and so what we're going to do is start by drawing a vector that goes from p naught to p. And the thing to notice is that that vector p naught p is lying flat in the plane, and so it has to be perpendicular to the normal vector that we drew a minute ago. Okay, so let's start by writing down the components of p naught p. Okay, that vector starts at p naught and ends at p, and so if we subtract the coordinates, we can get the components. So we're moving x minus x naught in the I direction, y minus y naught in the j direction, and z minus z naught in the k direction. That's describing the motion going from p naught to p. Okay, and then to get started in the process of finding an equation, we'll remind ourselves that the angle between these vectors is 90 degrees. They're perpendicular, and you might remember that since they're perpendicular, that means that the dot product of those two vectors has to be 0. We know that, okay, because of the fact that those two vectors are perpendicular. Or perpendicular. So that's kind of our starting point. Okay, and so we ask ourselves, how do we calculate a dot product? Well, dot products are about taking products of components. So if we want to take n dot p naught p, we're going to start by multiplying a by x minus x naught. That's going to be the first piece of the dot product. Plus b times y minus y naught, there's the second piece, plus c times z minus z naught. Okay, and on the right-hand side of the equation, we've got a 0. Okay, and so notice that what we came up with is an equation, and this is an equation that describes every point on that plane that we drew above. Okay, so we have just derived the equation for the plane that has point p naught, x naught, y naught, and z naught, and has a normal vector of n. ai plus bj plus ck. And the thing to maybe notice about this, this is a very useful observation. Notice where the a, b, and the c are in this formula. Okay, they're in front of x minus x naught, y minus y naught, and z minus z naught, and that a, b, and the c are the components of the normal vector. That will always be the case for a plane. These numbers a, b, and c will always tell you the components of a vector that's perpendicular to the plane. Okay, so let's go down and summarize what we discovered here. Okay, so 2 points that we'd like to make here. So if n equals ai plus bj plus ck is a normal vector to a plane and x0 is a point on the plane, then the equation of the plane is, and we're just going to rewrite the formula that we derived above. Okay, that's the equation. Okay, and again, remind you of the significance of the a, b, and the c. Those are the components of the normal vector, okay, to the plane. Okay, so that's our new formula for the equation of a plane, and I want to remind you that we had another formula for the equation of a plane. Okay, so another way to write the equation is to go back to the formula that we had before, the one that looked like this. Okay, if m is the slope in the x direction and n is the slope in the y direction, and we have a point on the plane, we can also write the equation of the plane like this. Okay, those formulas look very different, but they're both equations of planes. And you have your choice as to which formula you want to use if you have a problem that asks you to find the equation of a plane. The comment that I'd make is, depending on what information you're given, one formula might be easier than the other. And you have to decide based on the situation which one you want to use. Okay, so let's make a couple of notes here. Okay, just to tie all of this together. Okay, first, if you look at the equation of the plane that we just derived, you can actually rewrite that in several different ways, and one common way is to rewrite it in so-called standard form, to kind of multiply the a, b, and c through, and to put the constant term on the right-hand side. Okay, so we'll say it this way, by rearranging the terms in the first formula above, we can rewrite the equation of the plane in standard form. Okay, which looks like ax plus by plus cz equals d. Okay, it basically just involves multiplying through and putting the constant on the right-hand side. Okay, and then one last comment which might help you to decide which of these formulas you want to use. Formula 1 is best suited when you have two pieces of information, number 1, a normal vector, and number 2, a point. If you have those two things, or you can figure them out, then formula number 1 is probably the one you want to go with. Okay, so we'll say that this way. To use formula 1, to find the equation of a plane, okay, we need to know two things. We need to know a point on the plane, and a normal vector to the plane. Okay.